we are in the middle of our discussion of some frequency generation and second harmonic generation. We have studied the basics, leaving out most of the mathematics and most of the physics. So, we are trying to develop a user's perspective of this rather complicated subject matter. Now, today what we want to discuss is what are the issues that one needs to keep in mind when one wants to do some frequency generation or second harmonic generation, not with regular continuous wave laser light, but with ultrafast pulses. After all, the entire course is about ultrafast phenomena, and we need to be aware that it is important that we have to take care of certain parameters if you want to do nonlinear spectroscopy or even any nonlinear optical process using ultrafast pulses. It is not as if you can take out a nonlinear crystal from anywhere, say your millennia is broken, the continuous wave diode pumped solid state laser, maybe you have a millennia that has gone bad, you take out that some frequency well a nonlinear optical crystal from there and you think that you are going to use a femtosecond pulse using the same crystal, it will not work. So, today we are going to learn why it will not work and what is it that we need to keep in mind if you are going to do second harmonic generation, some frequency generation, so on and so forth using ultra short pulses. But before that, let us do a quick recap of what we have learned already. We have learned that this is the expression for the intensity of second harmonic light. What are the factors there? Of course, the second order nonlinear susceptibility is one that should be as high as possible, and as we have discussed without proving anything, that there should be no centrosymmetry if this is to be non-zero. If centrosymmetry is there, then in fact this is 0, forget about having a high value. Secondly, we said that it is better to have a large value of I0, provided I0 is not so large that there is material damage in the crystal. And finally, we worked with this term sin delta k L by 2 divided by delta k L by 2 whole square, where L is the length of the crystal and delta k is the difference between the k vectors, which boils down to difference in momenta of the combining light, right. And of course, since it is sin square theta by theta square, it is going to have a maximum at theta equal to 0. So, we will come back to this expression shortly, but what we said is that first of all L is limited by coherence length. We achieve delta k equal to 0 by angle tuning. We are going to expand, we have discussed it and we will do a quick recap in the next slide. And we talked some about the polarization of the second harmonic being perpendicular to that of the fundamental. And again we are going to do a little more detailed discussion about that. And this is what we had discussed in the previous module in very great detail, but once again not doing any real math. So, what we learned there is that there are two things that are important here. It is not only that the nonlinear optical crystal should have a high value of second order nonlinear susceptibility, but it should also be birefringent. What is the meaning of birefringence? The meaning of birefringence is that when light enters, polarized light, it should split into an ordinary ray or O ray with the same polarization and an extraordinary ray or E ray with perpendicular polarization. And the advantage of that is that you have crystals in which this refractive index for the ordinary and extraordinary rays are going to be different, right, and they are going to be different not only for the fundamental, but also for the second harmonic. So, we said that there are two kinds of crystals, negative crystals for which N0, NO, the refractive index for the ordinary ray is greater than or equal to that of the extraordinary ray, and positive crystals in which refractive index of the ordinary ray is less than equal to that of the extraordinary ray. And the other thing that one needs to keep in mind is that for ordinary ray, the refractive index is not dependent on the incident angle, whereas For the extraordinary ray, the refractive index is dependent on the incident angle. The polar plot for the refractive index of ordinary ray is going to be a circle, and that for extraordinary ray is going to be an ellipse. So, for negative crystals, this is what the picture is going to be, the one drawn in black. The circle, solid circle is the polar plot for ordinary ray. The dashed ellipse is the polar plot for the extraordinary ray. So, extraordinary ray polar plot is contained completely within the polar plot for the refractive index of ordinary ray. In positive crystals, it is the other way round, because here NO is less than equal to NE, whereas here NO is greater than equal to NE, all right. And then we said that let us consider a situation where the refractive index is less for the second harmonic compared to the fundamental. Then you get a similar set of circle and ellipse for the second harmonic, but they are going to be smaller in size. And then since we have an ellipse and we have a circle, we see that in this particular angle of incidence, the circle for the second harmonic overlaps with the ellipse for the fundamental, which means the refractive index of the extraordinary ray of the second harmonic is equal to the refractive index of the ordinary ray for the fundamental for that particular angle of incidence. And that is when the refractive indices are matched. So, phase matching is achieved, the conservation of momentum is assured, and that is when you get second harmonic generation. Okay. So, this is what we had discussed in the last module. I thought we will just recap once again, because it is not very easy, at least for us chemistry students to understand maybe. So, is there any question so far? Are you? Yes.
The case of ordinary ray and extraordinary ray.
Yes.
Fundamental and some generation. If the refractive index is ordinary ray or extraordinary is very less, they will not cross the. But we are having.
So, I think what he is saying is that if the refractive index is very small compared for the second harmonic compared to the ordinary ray, then maybe there will not be any overlap. If that is the case, there will not be any second harmonic generation. We will not get second harmonic generation in that case. There has to be an overlap, otherwise second harmonic generation is not going to happen. It is not enough to take a non-centrosymmetric material. Just because your material is non-centrosymmetric does not necessarily mean that it is going to be NLO active. Okay. So, in fact, very few examples of materials are there where you are going to get second harmonic. That is why they are so expensive. They are not so easy to make as well. Okay. All right. And then we said that it is possible. So, what are we doing? What happens when we change the angle of the crystal? Essentially, it is difficult to change the angle of incidence, because then the entire optical path will change. But if we rotate the crystal, then we essentially play around with the optic axis of the crystal and thereby change the angle of incidence without having to change the direction of the light beam. Okay. That is the trick. So, angle tuning, that is how it comes, and we said that it is possible to have crystals that are not uniaxial, but generally nowadays unless you have some very specialized application, there are plenty of good uniaxial crystals, positive or negative crystals, which you could use. So, generally one would use uniaxial crystal unless there is some compelling reason to not do so. And now I want to show you this table that you can actually find in Wikipedia. There are other ways of representing the same thing, but I like this table particularly because it introduces the terms that we are going to use in the next module when we talk about optical parametric generation and amplification. It introduces the terms pump, signal and idler. And why pump, why signal, why idler? The reason is historic. They are used like that. It is like SPDF orbitals. Why are they called SPDF and not ABCD? What is S? What is P? Remember, we are digressing a little bit. sharp, principal, diffuse, something like that, right. So, those are ancient terms which people have completely forgotten the relevance of. So, here also more for historic reasons, what we say is that this is basically a 3 color process, right. We are talking about some frequency generation, special case of which is second harmonic generation, right. So, we can say omega 1, omega 2, omega 3, right. So, what we are saying is the out of these 3 kinds of light, the one with the smallest wavelength is called pump. The smallest wavelength is called lambda p, p for pump. The one with the largest wavelength, longest wavelength is called the idler. Okay. It has nothing to do with laziness or activeness of the light, it is a name. What it means is, idler means out of the 3 beams that are there, idler is the one with the longest wavelength, that is smallest energy, and the intermediate one is called lambda s, s for signal. Okay. So, please remember this, highest energy is pump, intermediate energy signal, lowest energy idler. Okay. And also please do not miss the less than equal to signs. Sometimes it is possible that say idler and signal might have the same values. In whatever we have discussed so far, it is not very logical to say that pump and signal will have the same value, but idler and signal having same value, we have encountered that already, is not it? When does idler and signal have the same wavelength? In case of second harmonic generation, lambda I equal to lambda s, right. So, that is all that it is. So, please remember this, lambda p less than equal to lambda s less than equal to lambda I, that is all. Now, the crystals are classified into type 1, type 2, sometimes they are classified as type 3, type 4, type 5, type 6 and so on and so forth, depending on the relative polarizations of signal, idler and pump. In our case, please do not forget, so in the discussion so far, pump is what is being produced, okay, right. What is the meaning of pump in the discussion that we have had so far? Pump means some frequency or second harmonic, right, that is being produced. So, what this means is that if you have a signal with 0 degrees polarization and idler with 0 degree polarization, they are going to give you the some frequency which will have polarization at 90 degrees. Okay. 0 and 90 are written as O and E respectively. Okay. So, as far as some frequency or second harmonic generation is concerned, if you have same polarization of the combining light, the 2 combining lights, degenerate or non-degenerate, then we have already discussed the case where you are going to have perpendicular polarization of the light coming out, the some frequency or the second harmonic. So, that is called OOE kind of phase matching. Now, please do not get confused here. The problem is, since I have written pump first, you have to read from right hand to side to left hand side, opposite. So, type 1 phase matching is also called OOE phase matching, meaning 2 light beams of 0 degree polarization are going to combine to give you some frequency of 90 degree polarization. Of course, you might as well call it EEO, means the same. In fact, you see OOE is called type 1, EEO is also called type 1. Only if you want to differentiate between the polarization of the incoming light, whether you want to specify that it is horizontal or it is vertical, then you call this type 1 and you call this type 8. Okay? And the discussion that we have had so far is actually of type 1 phase matching, right. And will you agree with me if I say that when we talk about second harmonic generation, then it is going to be type 1. I will clarify the statement a little more, maybe expand the statement a little more shortly, but in the discussion that we have had so far, will you agree with me, second harmonic generation, unless you separate the beams, rotate the polarization of one for some reason, the light that goes in, it has the same polarization, right? You are mixing light with itself, the input light with itself. So, that is why if it is O, then OOE is what you will get, if it is E, then EEO is what you will get. But there is another kind of polarization, type 4 and type 5. Type 5 is also called type 0, where you have EEE, OOO. That means there is no change in polarization. When will that happen? When will no change in polarization happen? When a circle overlaps with a circle, or rectangle overlaps with, sorry, not rectangle, ellipse overlaps with ellipse, right? Right or wrong? Why did we get OOE earlier? Because the refractive index, polar plot for refractive index of the O ray of the fundamental, sorry, E ray of the fundamental overlapped with the polar plot of the O ray of the second harmonic. Okay. Now, relative sizes can be different, right, depending on which material it is. Depending on that, it is possible that one rectangle, one ellipse will cut another ellipse. Okay. Then you get EEO kind of thing. And then if you mix two different lights, now if it is two different rays, it can be omega 1 plus omega 1, but suppose you have taken that light and you have rotated the polarization by 90 degrees and combining, then you are going to have OE. Then if it is type 3 or 2B, you will get E polarization. If it is type 6 or 2B or 3B, you will get O polarization. Okay. So, there can be many combinations depending on what kind of whether the crystal is positive or negative and what kind of crystal it is. There is a compendium of which crystal is of which type in this book that we are studying, you can look it up. Okay. But it is important to know this, because polarization does have an important role to play in any nonlinear optical application that you want to work with. Okay. Right. So, these OOE or EOE, this you get for negative crystals, and this are usually obtained for positive crystals. This way you can look at many different combinations. And now, let me show you some example. So, these are some examples. KD star P, what is that? What is KDP? What is KTP? Homework, I will not tell you, you have to find out. The only thing I will tell you is that star means it is deuterium instead of hydrogen. But please find out what is KDP, what is KTP, what is LBO, BBO perhaps you know, beta barium borate, but you should know what this means. And what is this? LiNBO3, lithium niobate, right? Lithium niobate. So, these are all different kinds of phase matching crystals. Last three are type 1, first two are type 2. Okay. These are examples, there are other examples as well. Now, the question is which of these will you use? Will you use type 1 or type 2? As you see, what some other parameters are there that become more important than type 1 or type 2 when we want to talk about using ultrafast pulses. Okay. So, to understand that, once again let us go back to this expression that we had written a little earlier. Which parts of these this expression are going to be helped by ultra short pulses and which parts are going to be made more difficult? First of all, we have discussed earlier that ultra short pulses have high intensity. That is one feature. And second feature is that it has a spectral bandwidth. Yeah, spectral bandwidth. So, is that good or is that bad? High intensity is good, is not it? Because here you have this factor of I0. So, laser pulse, if you use ultra short pulses, then at least this I0 square is going to be high anyway, and we know why. We have discussed that already. Now, spectral bandwidth, is it good or is it bad? I am telling you it is bad. Why is it bad? What is the discussion we have had so far? We said, remember the k vectors? Yeah, this k is written here. So, the entire discussion was based on the fact that you have to have an exact phase matching, that is delta k has to be equal to 0. Now, what do you have in a pulse light? Is it monochromatic? It is not. What does that mean? It has many colors, many different what we call plane waves. A plane wave is essentially a monochromatic waves, where you have these parallel planes that define different amplitudes, different phases. Okay? So, this is not a plane wave. We will discuss maybe in the next module what it is, but this is a problem. How are we going to achieve delta k equal to 0 when there are so many k's? You get the problem? It is a problem. Okay. So, the problem is that you have to somehow achieve phase matching for the entire band. How will you do it? Well, nature gives us a way out, fortunately, and from this expression, can you tell me what the way out is? What is a natural way out? Natural, that word is a hint. If I want to plot this function I to omega, what will I get? Will I get a delta function? Then what is the factor that yes, what is the important factor in this discussion? Sin square theta by theta square. So, that has some finite width, is not it? Remember in our discussion of line width and all, sin square theta by theta square is the minimum line width that has to be there, even if you have two specific states, and that is what gives you natural line width to spectral lines. So, this is the plot really, remember. So, the thing is this, here at this point sin square theta by theta square equal to 0, but you do have a width, all right. So, even this is not exactly 0. So, if you consider the width of this function and all, it turns out that it is sufficient, you can manage to get phase matching provided delta k into L is less than equal to 2.78. Okay. No, this 2.78 just comes from numerical solution of this problem. I cannot write a formula and say that this is why it is 2.78, difficult to do that, right. But if you look at the pulses, it turns out that you are okay provided delta k into L is less than equal to 2.78. Okay. Now, what is the meaning of delta k once again? Delta k means basically difference between the k vectors, right. So, if you have many k vectors, you will have several delta k values within this limit. So, here if you read this ancient paper, you will see that okay, what does each k characterize? It characterizes one particular plane wave, right. Now, that particular plane wave is also characterized by a characteristic frequency. So, what this paper does from 1968 is that it starts from this delta k dot L less than equal to 2.78 and works out the expression for delta nu. The nu is something that we understand better, and nu is something that we work with a little better, right. So, we will not do the derivation, I will just show you the expression delta nu, where delta nu is nu minus nu 0. What is nu 0? The central frequency. So, delta nu minus nu 0 is only half of the band, right. So, nu minus nu 0 has to be less than equal to 0.221 by L multiplied by lambda f dn d lambda f, f stands for fundamental, minus lambda second harmonic dn d lambda second harmonic, reciprocal of that. What is dn d lambda? What is n here? Refractive index, right? And we know that refractive index is a function of frequency. dn d lambda is the rate of change of wavelength with respect to rate of change of refractive index with respect to wavelength, that is all, okay, gradient. Okay. So, this is what it is. So, now from here, if you know which fundamental wavelength you are dealing with, and dn d lambda for fundamental as well as second harmonic can be known experimentally from for the material, and I hope you understand that dn d lambda for fundamental or dn d lambda of second harmonic is going to depend solely on the material that you are using. Okay. And it is not very difficult to work out. You take thin slices of the material, see how much of change in refractive index is there, and you can work it out. So, from there, for a 1 centimeter KDP crystal, it turns out that delta nu is 20 centimeter inverse, whereas for 1 centimeter lithium niobate crystal, delta nu is only 0.5 centimeter inverse, but then I cannot just stop here, I have to say which wavelength it is. It will depend on lambda fundamental, lambda second harmonic also. So, the wavelength that we are working with is 1064 nanometer. What is the claim to fame of 1064 nanometer? 1064 nanometer is a magic number. What is it? Yes? Is the fundamental emission of Nd:YAG, right? One of the most popularly widely used lasers, 1064 nanometer. You will recognize the second harmonic better, 532 nanometer. So, if I want to convert 1064 nanometer to 532 nanometer, which material would be better if I am using a pulse? Should it be KDP? Should it be lithium niobate? Let us close this module on this note. We will come back in the next module and we will discuss from this point on.